Thanks for the invite. I'm very happy to be, at least virtually, with you. So when I received this invite, I was thinking about what type of topic would be quite interesting to see that kind of blends both a more foundational element of machine learning, but also an application that you don't see very often appearing, say, in publication and everything. But before that, perhaps I can give you some brief introduction about myself. So I am the Interdisciplinary Director of AI of the University of Aberdeen. I have a strategic oversight of this area across the university. But when I'm not spending time doing more my admin role with my research hat on, I'm very much interested in both applications and theory of machine learning. So when it comes to theory of machine learning, I have a special interest on self-supervised learning, capturing neural networks, and domain adaptation. Of course, I have been working across other areas as well with several students, but these are kind of the three main areas where I would say that my heart is at the moment. Of course, when it comes to the applications, as you're going to see later today, nuclear reactors has been one of the main areas over the past 4 or 5 years because we had a European project. So whatever I present today, it kind of was developed as part of Horizon 2020 European project, and there were other 19 partners across Europe. But at the same time, I have several other projects funded by industry. For instance, I'm working a lot with Siemens Energy. We are having some work at the moment with soft food industry on the agri-food sector. But in the past, I've also had funding from other sources on refrigeration systems, healthcare, and other areas. So as you can see, I'm splitting my time, say 50-50 between more theoretical elements of machine learning and another 50 more on the application side. So when it comes to the topic of today's discussion, perhaps it's important just to understand what a nuclear reactor is and also understand the importance of that. So actually, most of the nuclear reactors that we have across Europe, including UK, they are actually arriving at the end of life. So they are old models, most of them developed during the 70s. So it becomes even more important to be able to predict or detect any anomalies happening in the reactor core. Now, what you see here in this image is a kind of a schematic diagram of a reactor, so a nuclear reactor. So pretty much that is kind of the structure of the reactor. So you have this kind of structure internally where you have the fuel assemblies. And practically you think that will be a very big structure, but actually in reality, we speak about, I don't know, 3 by 3 or 4 by 4 meters. That's actually the size of the reactor. Everything else is the structure that supports the cooling or other kind of safety mechanisms. But actually the reactor itself is quite small, and that is where you have the fuel assemblies, which you can imagine this is where you have the fuel of the reactor. And different phenomena happen within this structure. So within the fuel assemblies, this kind of 4 by 4 area. So the nuclear physicists and engineers wanted to monitor what's going on. They have some detectors. So the detectors, you can imagine that they might be both in core, so they're called in-core detectors because they are inside the core, and some of them can be ex-core detectors, which means that they are in the periphery of the reactor. They're not inside the reactor itself. So, but all of these detectors collect data and signals during the operation of the reactor itself. So you can imagine that a fuel assembly is like that. So a fuel assembly is like a collection of fuel rods. So that means that you have rods where you have the fuel inside, and a collection of rods create a fuel assembly. So then all the phenomena happening in the reactor happen within this fuel assembly structure. Now, on this 2D representation of the core that you can see on the left-hand side, that's kind of a schematic example where you can see in the periphery, you can see S1, S3, S4. These are the X-core detectors, but also you can see at the very center of the reactor, you can have the in-core detectors. And then you can understand that a rectangular is just a fuel assembly, and you can have a collection of fuel assemblies within the reactor core. Perhaps this example that shows an actual reactor, maybe it's a bit more enlightening. This is from one of our partners at EPFL in Switzerland, where we visited, I think, just before the lockdown a couple of years ago. So that is a training reactor. So it's not radioactive, which means that I think they call it like zero power or very low power reactor. So that it's more for training purposes. But actually, it's fair to say that what you see here is what you would see in reality if you were able to visit or kind of open a reactor. Of course, you can't, but let's assume that you could. So these are the fuel rods where you have the fuel going inside. So what happens in reality is that when they are monitoring the operation of the reactor, you have various phenomena happening in the reactor. Perturbation, which means like vibrations or any other kind of phenomena. And a challenge that engineers have in this context is how can you use all of this information to detect anomalies that happen in the nuclear reactor. So what we did as part of the European project, I was leading the work package that relates to machine learning. So there were other work packages that were more focusing on the physics side of things, like new models, new physical models, new ways of simulating data. So our objective was to use simulated data. So that was the first part of the project. So we use simulated data because, as you can imagine, it's not that you get extreme events happening in the nuclear reactors every day, right? So you have very few actual events taking place. So the big challenge is how can you still develop a system where you can simulate some phenomena and some events happening, but at the same time being robust enough to be deployed in a real life setting. And then, of course, that's an ongoing challenge. And spoiler alert, I don't say that we solved that problem, but hopefully we kind of contributed to kind of solving this problem perhaps in the future. But I think we had some very good progress doing something useful for the nuclear engineers. So the other thing that's quite important is to understand that when we have the data, the simulated data in particular, we don't only have one type of perturbation. So, and that means, without me going deep into the nuclear physics, you can imagine that you have different types of perturbation. So you can think of it as being different problems of the reactor. Now, these problems manifest in different ways. They don't manifest in the same way. And also because the reactor is a volumetric structure, so you have volume, it means that perturbations and all of these phenomena can happen in different areas of the reactor. It can happen, at the top of the reactor, or at the very bottom, or in the middle, or left, right. So it can happen anywhere within the structure. So there is a challenge not only to detect that something is happening, but also where it's happening. So then you have the problem of detecting the different events, but also localizing all of these events. Now here you can see in these figures, you can see some very simplistic illustrations of the perturbations in the core reactor. And it's fair to say that most of the data that we use as part of this project, and of course I'm going to mention later that we also use some real-life data, but when it comes to the simulated data, it's kind of fair to say that nuclear reactor physics is a domain where everything is very well documented. And why I say this, because perhaps as part of your studies, and perhaps you've seen that in other settings, sometimes there is kind of a battle between, simulated data and real data with respect to, are simulated data good enough, or are we oversimplifying? Are we kind of capturing all of the intricacies, all of the background information that you can evidence in real life settings just by using simulation? So there's always kind of this constant battle between whether simulations are good enough for developing any machine learning model. Now, in this case, though, because nuclear reactors are very well documented, it's a closed system, the simulations are a very good approximation of what's going on in the reactor. It's not a perfect kind of illustration, because there's always phenomena that happen because of the actual real-life kind of operation of the reactor, but they're a very good approximation of what's going on within the reactor core. The problem, though, is that, as I mentioned before, we don't have only a single, like one type of event. We have multiple types of events, which doesn't mean that they happen at different moments of time. So if you can imagine for a minute that time is a very static element, so you have in time one, you might have more than one perturbation happening at the same time, right? So it's not that if one perturbation is happening, nothing else happens. No, you have everything happening at a single moment of time. So then another challenge that we are having is, can we perhaps detect all of these phenomena at the same time in the reactor core? So The way we tackled the problem, because as you recall, I mentioned before that we have a 3D volume, so you have a voxel, if you think of that from more the image processing perspective. We thought that given that the perturbation happened somewhere in this 3D volume, and what we want to do is actually detect that the phenomena are happening and then localize where they're happening from. So actually the localization means that you want to say that event 1 is taking place or took place in XYZ location within the reactor core. So the way that we tackle this detection problem is borrowing kind of some concepts from computer vision, which is more on the semantic segmentation, which means kind of trying to kind of create a system where we link each pixel or voxel in the input space to a semantic class, which means like a class label. In this case, you can see a cyclist, and then you can have the cyclist and then the bicycle, and then you can understand that some of the pixels in the image correspond to a bicycle, some other correspond to the cyclist, and there's a background as well. So something similar we could apply to this type of problem that we are tackling here in a nuclear reactor. So we use a 3D CNN architecture in the unit type, which is a type of architecture that is used usually for segmentations. And I think that when the paper came out a few years ago, that was mainly for medical imaging, for segmenting lesions in medical images. But there's no, actually since then it has been used massively in different settings to do segmentation in images and in computer vision, of course. So actually what we try to do by adopting this approach is detect within the 3D volume reactor all the perturbations in different locations and create a way of actually saying to the nuclear physicist, you know what, I see that something's going on in the reactor at this moment of time and in this location. Please act, do whatever you do best, and try to prevent any disaster from happening, actually. So that's kind of the main thing. So our process had 2 steps. So the first step involved the use of the simulated data. And the simulated data in this case comes from a simulation tool which has been developed by our collaborators in Chalmers University of Technology in Sweden. So they have, I think they are pretty much the world pioneers in this area. So this tool has been validated. So we're not going to argue against how accurate this tool is, because firstly, we are not nuclear physicists, so we don't know the physics behind that. And secondly, it has been validated in some real life data as well. So we took it for granted that these data are as close to reality as possible. So the first step involved actually developing a model on this synthetic data. And the second stage was actually adapting this model that was developed with the simulated data to some real life measurements that they were made available to us. Because as part of this project, we had quite a few partners that some of them, they were nuclear plants. So across Europe, so I think we had in Czech Republic, we had in France, but also from some training reactors that are active, so they are real reactors in operation, but on different power. I think that was from Germany, also from one of the institutes there. So then the second part of our development involved how can we somehow adapt the model that we developed with the simulated data to the real life data. And then we developed a self-supervised domain adaptation methodology so that we could align these 2 different, you can call it, distributions of data between the synthetic and real plant measurements. So on the first stage, we had an encoder-decoder architecture where we have the encoded part that tries to extract all of this information that you have in the frequency domain data. So we're learning very good representation that can be useful for the downstream task, which the downstream task, of course, is detecting the different perturbations. And then we have the decoder component where actually you try then to take all of this information that was extracted to create a prediction mask, so that then you can say, okay, we have areas where we believe there are some events happening in the reactor core. And then the second stage is, okay, how can then use a regression type of model so that then you can return also the IJK where we'll show you at which part of the reactor you have the perturbation originating from. So that is a type of architecture. So I don't know if you can see well in your projector there, but I guess you can see the model. You can see on the left-hand side where is the input space, where in this case you have volumetric input that corresponds to the frequency domain data. So these are kind of complex data. And then you have a series of blocks that correspond to CNN convolutions. You have some paramite pooling blocks that kind of help you develop more robust features when you extract more information from the input data. And I guess a good indication is what you see at the very top of this diagram, which is not part of the model, it's just a schematic that shows the reactor, which it might appear blurry to you, but it doesn't really matter because what you see in different colors here is the different types of perturbations. So you can imagine that this kind of 5 different categories correspond to different events, to different problems in the reactor. So the purpose of what we try to do here is, can we actually detect all of these different events as accurately as possible? So the major challenge doing that, as you can imagine, and that's not unique to the nuclear reactor context, it's kind of common in other settings as well, in even medical imaging, for instance, is that you might be having lots of data for a certain class, or it could be that you have lots of data for a normal operation of the reactor, but you might be having very few examples of adverse events, so like problems in the reactor core. So a way that we try to mitigate that is that we use focal loss, which is part of how we can actually train the model. So that is part of the loss function of the model, so that we can try kind of to focus more on the harder examples that we want to classify. Harder examples in this case is actually the examples that we have very few data for, which is the events of the reactor. Because then we have, I mean, if you think of the simulation, we speak about terabytes of data. So you can simulate as many data as you want. And perhaps it might be useful to you to understand that when they simulate data, the part of the input to the simulation model is actually the nuclear reactor properties. That means that you have to take the dimension of the reactor, you have to take the fuel rods, and like all sorts of specific information for a certain reactor. And the problem is that all of this information is highly sensitive information, highly confidential. So nuclear reactor industry, I would say that it is one of the areas that everything is very well protected. It's almost as if it's like a defense sector. So so you cannot just send data through whatever you want and just exchange data with everyone. So it's very, very well regulated. So that's why, for instance, you will not see me today giving you real life plant data information, because first, I'm not allowed to do that. And secondly, I don't think even it would make too much difference for the machine learning part in our discussion. So then bear with me. So now, up until now, we've seen that we had input data, which are simulated data in the frequency domain. Then we developed a model, a 3D model, that can detect the perturbations that happen in the nuclear reactor and the localization of them. But the problem that we are still having is, if we have real-life data and they are different to the synthetic data, how can we actually develop a model that can be useful when it comes to detecting events in real-life data? So then we have the problem of simulated to real-life data adaptation. What we did was that we relied, as I said before, on the fact that the simulated data are fairly accurate. Of course, as I alluded to before, that doesn't mean that you capture all of the intricacies that you expect to get from the real-life data. But the biggest challenge, actually, that we had to face is the fact that real-life data, it's not that they are only scarce. It's not that there are few of them around. We don't have annotations for them. So I would say that this was by far the biggest challenge, because other than very few events that you might be having annotations for, then in a real-life setting, the nuclear physicists see phenomena happening in the reactor, but they cannot really know exactly what's going on. So they don't have a way of taking the data and being absolutely certain that this event happened in the nuclear reactor. And actually, sometimes it is the case in real-life settings that they see events happening, and they don't even know why they're happening. For instance, I remember still it was 2019, February, I was in Czech Republic, and I was working back home with one of the collaborators from the Post Institute in Switzerland, and he's a nuclear engineer, and I was asking him, how do you do your job like on a daily basis? How do you actually check the data? How do you develop models to detect any anomalies in real life? And he told me we don't at the moment. That's why we have this project. But what he mentioned, that I'm still thinking about that, is that we observe phenomena happening in the nuclear reactor, but we don't know why they happen. And at first, at that moment, that's not very reassuring, right? So if you are, if you think that a disaster might happen, you don't know why, it's kind of it's not very reassuring if you're not a nuclear physicist. But for instance, he told me, you know what? Every 2 years, we remove the fuel rods, so we replace the fuel. And then when we put the new rods in the reactor, for the next couple of days, we see some phenomena happening just because we replaced the fuel rods. But we still don't know why, after we are replacing the rods, the reactor becomes stable. It doesn't become unstable to the unsafety kind of level, but still is not as we would expect it to be. So then, as you can imagine, going back now to machine learning, after I kind of put my brackets here. So the problem that we are having here is that we don't have annotations for the real life data. So then the challenge remains, how do we move from one domain to another? So that is where we decided to employ a self-supervised domain adaptation approach, where what we did was, again, in the absence of annotations, is that we said, okay, how can we bring those two distributions together, like synthetic and real life data? So as you know, self-supervised learning is a process where you try to use unlabeled data and through different approaches. So in the very beginning of the self-supervised learning, it was very common to have this kind of auxiliary tasks about rotations, about jigsaw puzzles and everything. But we've moved since a while now, for instance, with a simpler paper, which was on the contrastive learning. Then you have some contrastive learning methods, and then non-contrastive learning methods became popular, and now you have masked type of supervised learning approaches. But what we did is that we didn't try to kind of overcomplicate our lives in this case. So we thought that we can just employ some simple auxiliary tasks and then have the models try to align themselves because they were trying to solve the same problem. So then we said, okay, let's create our own labels and then have the two models try to align themselves by trying to solve the same problem. So very simple tasks, just rotation, flipping, and I think perhaps you can say that maybe the most novel, if you can call it novel, in this case, type of task was the fact that then we played with the different detectors. So going back a few slides, I mentioned that the engineers monitor the reactor through detectors, so like sensors. So then we said, okay, can we just start removing sensors and then create a system where it predicts which sensor is missing in different areas of the reactor? And then if you have both models trying to do that, then somehow then you try to align the two distributions together. So that's actually how the model looked like. As you can see, the base model, so the backbone model, looks very similar to the one I saw before, because it is similar, because we kind of used the model that was developed for the simulated data. But then the new thing that we are having is that we have another input which corresponds to the real life data. And then if you go to the right-hand side of the model, you can see that at the very top, we have the downstream task. So the downstream task is the detection of precipitation. So that's kind of the supervised task. But then at the bottom, in the three other blocks that you see, you have the auxiliary tasks. So this is the self-supervised learning component. And that's why you see now two arrows, because at that point of the network is where you have both the simulated data and the real data. And that is where the alignment of the distribution is taking place. So actually, we got very good results. So especially for the simulations, we have very good results. So our kind of partners in the nuclear industry was very happy with what we got, because that was actually the first project that ever considered that. So we're the first ones to actually put our hands on this type of problems when it comes to machine learning approaches. Now, in this table, you can see the different types of participation. Again, because this is not an engineering talk, and I think you have a parallel engineering talk. Maybe I should go to the engineers and then have a chat perhaps on that. But anyway, so you can see the different types of observations here. But the first two columns is the number of combinations, and the combination means what I mentioned before is the multiple perturbations. So the number of combinations refers to how many events do we want to say that we have at the same moment taking place in the reactor. And then the number of detectors is actually how many detectors, so how many sensors we consider to do that. So you can see in some cases the accuracy was very high, and our partners were very happy with that. Now, I mentioned on the heading of the table something about pre-convoy. So convoy in this case is just a type of reactor. So it's not something kind of sinister. Just this is how the specific reactor is called, pre-convoy reactor. Now, this is an example of the prediction mask. Now, if I had a student of mine looking at that, they would be telling me, oops, but the prediction mask, which is actually the first one appearing on the left, and then the second one is the ground truth, and then you have another block of the same. So actually, the first from the left is a prediction. Right next to that is a ground truth, and then you have for different types of perturbations on the other side. Someone can say, yeah, okay, it seems that you predict well, but still I see quite a few errors. And that would be a fair point to ask, but you have to remember that when we develop a machine learning system, usually, especially if it's a binary problem, we say, okay, unless there is some sort of background information why a class is more important than another class, then you say, okay, sensitivity, specificity for me is kind of the same thing, but you can think that in a nuclear reactor setting, we would rather have many false positives, which means that we would rather to over-predict something than under-predict something. So it's not a problem for the nuclear engineer to say, yeah, tell me more, and then I can say, okay, you were overly cautious by telling me that many phenomena are happening but they're not happening, rather than having false negatives where we say nothing's happening but something's going on. So then we had to tune the model in a way where we wanted to capture the phenomena, albeit sometimes we're overly, over-predicting some of the areas. So that's what you see actually here. You see that we were very accurate in detecting the events, but we were over-predicting some of the events that were not taking place. Now, the problem that we have when we are using real data in the absence of ground truth is how do we know that whatever we predict actually is correct? So there are some proxy ways of doing that, and one way is actually using the maximum mean discrepancy loss, where it gives us an idea through comparing the different distributions, like, are they aligning together? So that gives you an idea how well aligned are they. So then that's kind of a proxy measure where you say if it's reducing, it means that they are closer together. So we are happy that something is going on there that is positive. And then the other kind of gold standard way of, which is not gold standard in the context of what we use in machine learning, but we say gold standard is the ground truth. So if I match that, either I'm overfitting or I'm very correct in what's going on. But for the nuclear industry, gold standard is signal processing. So they are have developed techniques where they extract some information from the signals, like with the signal processing approaches, and they kind of create heat maps, like the one that you can see at the bottom of this, at the second figure at the bottom, where you can create a heat map where you can actually, see what's going on with respect to the signal processing element. So then you can have a visual understanding of any areas where your models might not be predicting very well with respect to what you are expecting to get. And here it is an example again, but in this case is the real data as well. Whereas in the previous case where we saw similar plots where just the similar data. So you can see similar phenomenon here where through this process and using the signal processing as a proxy to say that what we are predicting is correct, then we were quite accurate even predicting events in the real data. But again, bear in mind that it's not the same as was the case with simulated data. So our confidence here is based on proxy measures, not actual ground truth, as you would be expecting to have in other contexts. So just to kind of summarize what I spoke about today. So this project was about detecting rare events and anomalies in the nuclear reactors. So to do that, we spent 4 years practically. It was a European project. So we had several partners that provided us with different simulated data. And then we developed our machine learning models to detect the events and also localize these events within the nuclear reactor. And then we use some real-life data, so from real-life real plants, real nuclear plants, to actually develop some methods called self-supervised adaptation to align the simulated and the real data domains to be able to create a system where it's as robust as possible in detecting events in real-life data. Now, again, our main challenge was that we don't have real-life data that are annotated. So that remains one of the biggest challenges. That's why that is part of what we are currently trying to work on. So we are trying to kind of develop a new proposal that will incorporate these components. So that how can we move to a system where actually we can collect some annotated data. But also what we want to consider is, okay, because today I haven't touched at all the element of the user. So as you can imagine, having users from the nuclear industry and then machine learning engineers, you have to find a common language. And that's not easy sometimes. But at the same time, you want users to be confident that if they use a tool, they know how to use it, they know the limitations, they know they can trust it, and so on. So then you have the elements of how explainable this method is, how you can interpret it, how trustworthy it is. So then we think that the next step could also involve these elements of interpretability, because it's important to find a way of doing that for gaining the user's trust. Now, of course, whatever I described today is not my own work alone. Of course, I had a part of that, but there were a huge team behind that, and several PhD students of mine, some of them finished, some of them still finishing, were involved in that. So it was a collaborative effort, and so we managed to achieve some good results because we were actually a very nice team and we worked very nicely together. Thanks, everyone. I'm happy to take any questions you may have. I know that you are operating under very strict schedules and you have student presentations to follow on, so I wouldn't be offended if you were telling me that there's not much time for questions.
So do you have any questions? Any questions from audience?
From the online ones?
Okay, from the online participants, is there any question?
Yes, there is one there.
Hi.
Yes, Abdullah, go ahead.
Can you hear me? Thank you for your nice presentation. I have a question about the adjusting your neural networks to be suitable for a real world data. I think in the slide 21, you said about the auxiliary, I don't know, features. Can you go to the, yes, please. 21. Slide 21, please.
21 is this one, but it doesn't have the auxiliary features. You mean, I guess you mean this one, 19. Is that?
I don't know. I am see 26 of 27. I don't know. Let me go 21. Okay, 20. Yes, 20.
This one.
Yes, there is that network.
Yeah.
You speak about this auxiliary output. Am I right?
It's an auxiliary output. Yeah. So you create artificial data, input and output, and then that becomes part of your pretext tasks that you have for your model. Yes.
Okay. What kind of label or mask you have been used for this auxiliary output?
Exactly. So that's exactly the point. So when you develop a self-supervised component of the model, you create artificial labels that correspond to the task that you want to achieve. For instance, you use the input data, say that you have, as I said before, the volumetric data which correspond to the reactor core, which are frequency domain data. And then because you have a volume, then you can split the volume and you can start rotating the data. Then when you rotate the data, you know how much you have rotated them. So you label it accordingly. So you say, I rotated 90 degrees, label it as 90 degrees. You rotate 180, you do it for 180. So then you create your own labels. And then you have the two parallel networks trying to predict exactly the same transformation. So by doing that, then what you are trying to achieve is align the distributions together. So you create, as a machine learning researcher, your own labels. And that is what we do as part of the self-supervised learning component.
Okay, therefore they are, in fact, some rotation or some change on the main mask.
You can decide whatever tasks you can involve. For instance, we also had a missing detector. So then instead of doing any transformation, we actually were removing data from different detectors, and then you were tasking the models to say, can you detect which of the detector is missing? Can you kind of predict all? So you can create other tasks if they are relevant to the task. So it's not that only these tasks, these 3 tasks are the appropriate ones. So one could have created different ones as well.
Okay, thank you. Does this improve the result? This auxiliary automation?
It's not only the yes and no. So why I say yes and no is the fact that when we do that in this case, and we have the real life data, because we did that for the real life data, you see an improvement, but because you don't have the ground truth, you can only have a proxy way of understanding whether things have improved or not. But yes, a quick answer would be yes. We saw that there was an improvement in the results.
Okay, thank you. Thank you.
Okay. So if you do not have any question, so let's wrap up the session of keynote speaker. On behalf of management, the whole advisory team, and as organizing committee of myself, I would like to thank Dr. Georgios Leontidis for this wonderful session. And I guess your valuable insights are really inspiring to all the attendees. And thank you so much. And we are really privileged to have you in our conference platform.
It was my pleasure. Thanks for the invite again.